Good morning, one and all. I am Jeevan KM, doing my research in the field of hexagonal image processing under the guidance of Dr. S. Krishnakumar. Now I welcome you all to my presentation titled An Image Steganography Method Using Pseudo-Hexagonal Image. And this is my outline of presentation: introduction, literature survey, proposed method, result and discussion, and finally conclusion. We all know that the common representation structure of a digital image is using a rectangular grid of square-shaped picture element, and this picture element is known as pixels. And in this type of representation, every pixel has to be identified by its row and column. And also, the pixel adjacent to one center pixel have different distances to the center of the center pixels. Here you can see in this figure, the distance from the center of the center pixel to the center of each corner pixel is represented as root 2, provided the distance from the center of the center pixel to the center of the other neighbors are taken as unit 1. The first digital image is made in 1957 by a scientist known as Rachel Kirsch, and he used his own son's image to make the first scan or the digital image. And at the time of making this first image, the team used square sampling. That is, they used square-shaped small elements. They used square-shaped elements to represent the digital image. But later, in an interview given to a science magazine, he himself says that the square was the logical thing to do. Of course, the logical thing was not the only possibility, but we used squares. It was something very foolish that everyone in the world has been suffering from ever since. That means, or from his own words, we can say that there may exist other possibilities. That is, there may exist other shapes for representing an image. There exist three different schemes that can be used to tie a plane without overlapping among the samples and gap between them. The tessellations are the tessellation with squares, tessellation with hexagons, and tessellation with the regular triangles. And first case, that is a tessellation with square. This we are using nowadays, and this can be represented by using a Cartesian coordinate system. And in the case of triangle, it yields a denser packing than the square cases. This points out that more information is contained in the same area of the image. And finally, we have a hexagonal tessellation, and it is believed to be the most efficient tessellation among the other because it is having a various of advantages. So now let us see what are the advantages of hexagonal structure. And these are the some advantages, and I am not going to detail it because of the time constraints. The advantages are small quantization error, consistent connectivity, equidistance, greater angular resolution, and higher symmetry. And the other advantage is a property known as the isoperimetry. And a hexagon encloses more area than any other closed planar curve of equal perimeter except a circle. And this is known as the isoperimetry property. That means the hexagon is having a more area compared to any other closed planar curve having an equal perimeter. And this implies that, or this property implies that the sampling density of a hexagonal lattice is higher than that of a square lattice. In addition to this, there's some other motivation behind using a hexagonal resampled image is connected to the human visual system. That is, the retina of the human visual system or the human eye closely resembles a hexagonal grid space. As we know, the retina is a part of a human eye, and when a human being viewed an image, when an image is being viewed by a human being, then it is imaged in the retina. That is, the scene is imaged in the retina. And in the retina, we have two different cells, rods and cones. And these rods and cones are arranged in the retina in a hexagonal grid shape. This is shown in the figure. Here you can see that the rods and cones is having a hexagonal shape, almost hexagonal shape. And again, the research done in animal vision also clearly demonstrate that the arrangement of rods and cones are having hexagonal tesselation. So, if we could able to represent a digital image using a hexagonal structure, then the computer vision or the machine vision will be as close to the human vision. That is why the researchers are going behind this hexagonal image processing. Even though the hexagonal structure is having its own advantages, even now the image processing in hexagonal domain is in infant stage. This is because of the non-availability of hardware for acquiring hexagonal images. That is, every hardware nowadays available for acquiring the digital images having a square-shaped pixels. Therefore, for performing an image processing application in hexagonal domain, we need to resample or we need to convert a square-shaped pixel image to the corresponding hexagonal domain. And some methods are nowadays available for this resampling or the conversion from a square-shaped image to hexagonal pixel image. And out of this, I'm just explaining now one simulation method which is known as a pseudo-hexagonal structure, because in our work we are using a pseudo-hexagonal structure image to hide an image. So this structure was proposed by Woodridge and Stuckey, and in this type of simulation, a hexagonal pixel which is called a hyperpel is simulated using a set of many square pixels as shown in the figure. That is, a single hexagonal pixel is created using a many number of square-shaped pixels, and the square-shaped pixels are taken from the original image. That is, this image is converted back to the image with the hexagonal structure. And here we can see that a single hexagonal image consists of, or it is a combination of many square-shaped pixels. And this square-shaped pixels which is involved in the generation of a single hexagonal pixel is termed as subpixels. Now, these are about the hexagonal image processing. And now let us see some introduction about the image hiding or the steganography. The word steganography is a word of Greek origin which means hidden writing. And this word consists of two parts, steganos, which means secret, and graphic, which means writing. And in every image hiding technique, there exist two images. One is known as the cover image, and the other one is known as the secret image. And the cover image is nothing but the image in which the message or the secret image is going to be hidden. And the secret image is the image going to be embedded in the cover image. Now let us see some literature survey. That means some of the works included in the steganography method. Most of the image steganography method can be broadly classified into spatial domain method and the method based on the frequency domain. And in the case of spatial domain, the method is based on the direct manipulation of the pixel in an image. And in the case of frequency domain method, the modifications are done on transformed images. And in the case of the spatial domain as well as in the case of frequency domain, the most of the techniques are based on the LSB substitution or the modification of LSB of the cover image. And in the case of spatial domain, LSB replacement or the LSB matching are there, and the frequency domain, normally we modify the LSB of a non-zero DCT coefficient of a cover image. This actually, I am not explaining all the present works. This is just for understanding what is nowadays existing. Now let us see the proposed work. In our proposed work, we have come up with a method of hiding an image in a cover image, where this cover image is represented using a pseudo hexagonal structure. And please keep it in mind that only the cover image is in pseudo hexagonal structure, and actually the secret image is represented using the conventional method. And also we are using an algorithm which is termed as JK algorithm, and this algorithm is used to create a pseudo hexagonal structure from a normal or the conventional image. And this, in the case of this algorithm, the letter J represents the first letter of the first order, that is G1, and K represents the first letter of the second order, that is Krishna Kumar. And this JK algorithm is for generating a pseudo hexagonal structure, and it is not for hiding the technique is used only for generating the pseudo hexagonal structure. And this JK algorithm is already published in an international journal, and so again, because of time constraint, I am not explaining that JK algorithm in details. Anyway, just for understanding what is this, the square pixel of the image is actually converted to a hexagonal pixel using many number of square pixels. And for that, what we are doing is, first we take a square pixels, and this is actually duplicated means we generated 72 subpixels from the pixel what we are taken, and each subpixel is having a same gray level value, which is same as that of the square pixel we taken for converting. And out of the 72 pixels, we are using only 56 pixels for representing a hexagonal structure, as shown in the figure. The pixels which is numbered as 1 is used for generating the hexagonal pixels, and all other pixels which is numbered as 0 is eliminated. So we are getting approximately a hexagonal structure using this square pixels, square shaped subpixels. And now this hexagonal pixel, which is a combination of 56 square shaped subpixels, are used as the cover image. And now, just for an example, or this image or this figure represents a hexagonal structure obtained from a square shaped pixels of gray level value 187. So we can see that each subpixel is having a gray level value is 187, or we assume this subpixel is having a gray level value which is same as that of the square shaped pixels. And now we are going to hide or embed another pixel which is taken from the secret image into this hexagonal structure. The step is explained like this. So consider one pixel of secret image with gray level value 147 and one cover image pixel with gray level value 187. So as in the previous slide, the cover image pixel is represented like this. It consists of 56 number of subpixels. And so let's take this Sij, that is secret image, pixel of secret image is having 147 gray level value, and the cover image is having a value 187. Now this pixel is going to be hidden in this hexagonal structure. So this is just the binary representation of 147 and 187, and this figure I represent the binary representation of 147, and this represent the binary representation of 187. And this is the steps which is included in this method. That is, the first show represent the binary representation of a subpixel value. That is, we consider a first subpixel, it is having a 187, to hide the LSB of the secret bit that is having a pixel value 147. As we know, it consists of 8 bits, and starting from this is the LSB, and starting from this, and this is the MSB. So as a first step, we are going to hide this single bit in the first in this particular subpixel that is having a value 187. Actually, we can use any rows or column for hiding the pixel value, but in this example I am using this particular column for hiding the secret image. So this is the binary representation of the subpixel value, and first bit of the secret image is again 1. Now we need to replace this LSB value, and in place of this LSB value we want to put this particular one. So this is the bit to be replaced, and in place of this we need to put this particular one. So this one is placed here, and again come to the second bit. Second bit of the secret bit is again 1, and the second bit is of the secret bit is hidden into the second subpixels. So we again take the second subpixel, and the second subpixel is also having the same value 187. So this is represented here, and again this one needs to be replaced, and we want to put the second bit of the secret bit, again that is 1 here, that one is to be put at this position, and it continuing until all the 8 bit of the secret bit is placed in the particular position. So I would like to say that we are using 1, 2, 3, 4, 5, 6, 7, 8 subpixels of this column for hiding each bit of the secret image. That is, first bit of the secret bit image is hidden into the first bit of the first subpixel, and the second bit of the secret image is hidden into the first bit of the second subpixels, and finally the 8 bit of the secret image is hidden into the first bit of the 8 subpixels in this particular column. So here I can say that actually we hide each and every bit, that is the entire 8 bit of the secret pixel is hidden into the cover image. And for and again we have to notice that we just replace a single bit from each subpixel. That means the value of the subpixel is not much altered. That again almost same as that of the original one. So after the replacement, the pixel values will be like this. That is here you can see that only just 1, 2, 3, 4. That is value of only 4 subpixels is altered, and that is again changed from 187 to 186. a single bit change, and therefore not much alteration is done in the cover image. That means the cover image, the property of the cover image is not much changed. And this is the process for hiding the entire bit. And now let us see the resultant discussion. This is pseudo hexagonal structure cover image obtained using JK algorithm. Here we can see that this image, and this is the enlarged version or the zoomed version. Here you can see that the pixels are of hexagonal shape. And this is the cover image after embedding the secret image, and here also you can see that there is not much affected by this embedding process. This cover image is same as that of the original image, because only a single bit of each subpixel is changed. And in this case, the figure A represent the secret image, and this B represent the secret image extracted from the stego image. That is, this is the image extracted after hiding process. Here also we can verify that both A and B are same, because we are hiding entire bit of each pixels of a secret image. And again, these are some examples using different figures. And this table represents the MSE and SSIM measured between the secret image before hiding and the secret image extracted. And in this case, for all cases, we are using a same cover image. Is taken example of avatar.jpg, and these are for different secret image. Here you can see that for each cases the MSE is equal to 0, and this SSIM has the maximum value 1. That means the secret image before embedding and the image which is taken back from the stego image is same without having any MSE, or the similarity is again 100% same. This table shows the MSE and PSNR measured between the cover image and the stego image for different secret image. And again, the cover image used is water.jpg, and again this much of images are used as secret image. And this is MSE, which is measured between MSE and PSNR, which is measured between the cover image and the cover image after embedding. That is cover image and the stego images. We are having a PSNR of almost 60s. And now come to the conclusion. That is, these are the conclusion based on the work. That is, the performance is enhanced using MSE, PSNR and SSIM, and in all these cases it is better. And if we so we can conclude that this hexagonal representation gives a better result, and this hexagonal representation helps the computer vision as close to human vision. Also, it will, we can say, it will give the missing cornerstone of artificial human visual system. Okay, and these are the some publication. These are my own publication based on our previous working hexagonal image processing. And more than this, actually I just include only 6. And these are the some references I am used for this presentation. Thank you for hearing.